playing with you a game. This game, I'm going to hide something in the grass. So I'm going to hide something in the grass. Maybe I'm going to hide it here, or I'm going to put it here. But let's say, of course, you don't know because this is the game. You don't know where I'm going to hide the thing. So let's say that I'm going to hide the things at this place. So I put something here, but I hide it. So now I'm asking you, you are at this place, I am hiding something. I want you to find. So what's the first thing that you are going to do? You need to look for it, right? But how you are going to look for it? Do you know how you're going to do first? Can someone tell me? You are having this direction, or you are having this direction. You are standing here. Let's say this is your XI. So normally for the human, what's going to be happening? Is that difficult? There's no one here. So let me before for the class, because if you stand this easy one. You're standing here, and I'm asking you to find the things that I hide in the grass. So what you're going to do? Can you hear me?
Yes, move to the left to the place that you hide it.
Yeah, but how you are sure that is it? How are you sure that you are going for the left first time? Or it's because I draw this one here, right? Okay, never mind. Let's change the game a little bit. Now, I hide something, and I'm asking you to look for it. Where you are going to go? Are you going to the right or you're going to the left? What are you going to do? There is something I hide. I put here in the grass. And I'm asking you, you are now in the middle, and I want you to find it. So what you're going to do?
Look around first and then decide where to move.
Perfect. Perfect. So can you please tell me what's your first move? You are going to look for it on the right or you're going to look on the left?
To the left.
Okay, so that's mean first time because you don't know where is it, right? So you're going to go for the, you're going to maybe it's not here. You're going to try to find it here. Maybe it's not here. Then you're going to try to find it here. Maybe it's not here, right? This is what you're going to do, right?
Yes.
So that's mean if the whole way to the left you couldn't find it, you will back again to the same position. Then you will start to look to the right. Or maybe we go here. We are going to do exactly the same way. We are standing on first essential place, or we are having essential value. Then we are going to look for our value of x of the root of the equation. Okay, so this is what we are going to do today. So we are calling our method today, it's the open methods. Why we are saying it's an open method? Open methods, it's based on a formula. So that formula just only require only a single starting value. So that's mean last week when we are talking about the bracketing methods, we are giving you the value of x lower and of x lower and x upper is here. Yeah, for sure you're going to find it. So the advantage of using the bracketing methods is there is no way you in any way you are going to find it. No matter how much or how many times you iterate, still you are going to find this value because you know it's between two values. But today we are talking about you are going to just only have single starting value. You are going to just only have xi, which is in somehow looks like you are here standing in the middle and you don't know where is the root. Is it on the right or it's on the left? Okay. So open methods is on a formula. It's just only require single starting value of x. This has a things, but no worry about it. It's based on a formula that so again a series like this. This person is trying to find what put in the graph. Trying
Sir, sorry, suara sir sekat-sekat.
to you from here to here. This one. This is what we call it here is a bracketing method because here it's x lower and this is x upper. So this is what we had learned last week. So we are saying that it's bracketing methods. It's the root it's between here. Today we are going to start with single starting value. So when you are starting with a single starting value, we are going to just only give you the value of x here. So you are starting with the x here. So if you are going to look on the right side or on the left side, if you look on the left side, you are not going to find the root. But if you also looking for the right side and your predictions of the value, it's like far away from the root. So this means you are not going to find the root. You already miss it. So this is what we're saying here. Sometimes the open methods, it's diverge from the root. This means you are not going to find it. But what's the advantage of using the bracketing methods? When it's converge, they do so more quickly than the bracketing methods. So that means it's the advantage of using open methods. It's more faster, a little bit of iterations, and more accurate than the practice methods. This is the advantage of using the method. Disadvantage that it is easy method. Here, no need for good thing is just only arrange so be on the if we are having this equation, we are going to rearrange it based on x squared. We're going to arrange based on x squared or 2x. In this example here, he arranged based on this. So x is equal to x squared plus 3 over 2. Then you start to solve. So simple fixed methods, what you need to do is just only rearrange the function so the x is going to be on the left side of the equation. It's an iterative method, same like the practicing methods. Maybe you need to get for 2 iterations or 3 iterations or whatever iterations till you are going to meet the value of error. So to calculate the value of error new minus the x old or the initial minus x over the x new. Okay. So let's see our first example here. This is our first example. To use the simple fixed point iterations to locate the root of this function. So this is my function. Okay. Your initial value of xi, it's equal to 0. So your initial value of x, it's equal to 0. So let's see now how we can solve this. So remember, fixed point, we just only rearrange the function. So we put x on the left side. So we take x, we put it on the left side of the equation. So in our case in here, we'll take this x and we put it on the left side of the equation. Okay. So this is my function. I rearrange by putting this x on the left side. So it becomes like x, it's equal to exponent negative x. My initial value of x is equal to 0. And this is supposed to be the true value. So the first thing what I'm going to do, I will put my initial value inside simple fix point. So at the first iteration, to get a new value of xi or the new x is equal to exponent negative 0 is equal to 1. Okay. So now, since I have a new value of x, I'm going to use it for the next iteration. So now when you go for the second iteration, to find a new value of xi is going to be equal to exponent negative 1. So I'm taking this value, I put it here. So the answer is 0.36. I will go for the iteration. So more is equal to find the new of it's equal to negative 0.39. So I'm taking this value. This is the answer. So 20. Point methods. Nothing to do, is just only rearrange the function so that x is going to be on the left side of the equation. Okay, I want you to try. I want you to try the example. I don't want you to make it all because you can see that you're going to iterate from 0 to 10. Just try it for 2 iterations only. Just get used to it and you can calculate the error. You can calculate the relative error and also you can calculate the approximate error. Can you just simply try these 3 iterations only, please. Take your time. I will give you about 5 minutes. If you have any questions, please do ask. Can someone tell me why the error at the first iteration here is we cannot calculate the error at this point? Can someone tell me why I cannot calculate estimate error at this point? Anybody have any idea?
There are no value before it.
Wow, you are brilliant. Thank you very much. Thank you. Because we don't have an old value of x. So at the first iterations, there is no value. So I cannot calculate the approximate error at the 0 iterations. But for the true value or for the relative error, yes, I can, because 0 minus the error, the true value over the 2 is going to give you 100%. I'm going to just only calculate the approximate. You cannot at the 0 iterations or because you know all that. Thank you very much. What's your name?
Howard.
Thank you very much. How? You're from C or E?
I'm from E.
Okay, thank you.
Welcome.
Okay, do you have any questions about the method? Any questions about the simple fixed point method? Is it clear?
Clear.
Okay, so let's say the methods. Actually, there are 55 methods. So it's the two graphical methods and something like what we learned last week about graphical methods. The graphs intersect with each other, you're going to find the roots. It's a simple way to see it with the example. What we do in here, if you are having a function, you're going to break the function into two parts or into two components. Then you are going to draw them separately. So let's say that this is a function 1, this is a function 2. So you are going to draw function 1 and function 2. And when they are crossing each other, so this point is considered is the root. Let's see it with the example. Let's say that this is my equation for negative minus x. So I'm going to break it into two parts. Let's say this is going to be y1. This part is going to be equal to y2. Okay, and this is the value of x of each part. So if x is equal to 0, so this means x here is going to be 0, so y here is going to be equal to 0. If x is 0 0.2, so 0 0.2, so this means y is going to be equal to 0 0.2, and so on. Okay. Try again here. If x is equal to 0, so y2 is going to be equal to 1. If x is equal to 0 0.2, so y is going to be equal to 0 0.18. So if x is equal to 0 0.4, so it's 0 0.67, and so on. Once you get these values, so you are going to plot this column of y, which is going to give you this red line. Then you are going to plot this column y2, so it's going to give you this curve. So this curve, both intersecting at this point. If your function, so if we draw a function, and its x-axis at one point, so it's crossing the x-axis at this point. So this point is the root. So when you are looking at this point and this point, they are exactly at the same location. So this is considered is the root at this place. So they are in the same position. That's all. Nowadays, you're not going to get any question from this part. It's just only a general information how to do it. Okay, so now remember our first things I said today is if I am playing with you this game using open methods, if you go to the left, maybe you're not going to find what I hide or the value of x, or you are not going to find the roots. So this is considered that you are diverged. Maybe if you go to the right, you are going to find it. So if you find it, that's mean you are converged to find the roots. Okay. So this slide in here is talking about conversions of the open methods. So if we are going to use the open methods, the converge and diverge could be happen in two types of mode. It could be happen in form of staircase or oscillating mode. So converge or diverge can be happening in staircase or oscillating mode. Let's say like this case, this is a convergence. The way that you are trying to find this root, this is a convergence because you are starting at xi, which is x0. So that means your next value of x is x plus 1. So you can see that it's in a form of staircase towards finding roots, or oscillating mode in a form of a circle, like this one is x0. So you can see from here, it's to oscillate around still. So x is x1, this is x2, and this is x3. Diverge also happen in the same way if you are trying to look into a different direction. So you can see from here, it's my root, it's on the left side, and you step to start to find it's going to the left, so you are going to find it. Let's say that you start your search, but you are going to the right direction. Of course, you are not going to find the roots. And these things also could be happening in a form of staircase. So interesting are just you are not going to find the roots. Okay, so remember that it's open methods. It could be converge, could be diverge. But now, let's say it's when you are trying to solve the open methods to find the roots, it's diverge. How you are going to overcome the problem? So let's say that like this is the case that you have. You start to look for the roots in a wrong direction. So of course in here you consider like you are diverged because you're not going to find the roots. The roots are supposed to be on the left side. You are just only looking on the right side. So how are you going to overcome this problem? To overcome this problem, the first one is choose different initial value. If my x initial value is in here and I'm going to look on the right, of course I'm not going to find it. So how about if I put this x instead of here, I put it here. My x0, I put it here. So if I'm going to go for the left, sorry, for the right, of course I'm going to find the root. So this is one of the way of to overcome the problem of diverge. Or to choose another methods, or to modify the function into another forms. Unfortunately, number one and number three, you are not allowed. When the question is coming to you, we are going to talk about the method to use. So you're not allowed, you cannot modify it, and you're not allowed to choose any different initial values. You have to use what we are giving to you. So the only things that you can do is just only number two, which is modify the function into another form. What does it mean? Let's back to the first example here. Okay, we are saying here is the simple fixed point methods. What you need to do is just only you need to rearrange the function so x is going to be on the left side of the equation. Like for our case in here, we choose this x. We choose this x to be arranged to be on the left side, so we are having this form of a function. So let's say that you are taking this form of the function, then you start to solve. So this is x, and this is the function of x. Calculate error. You start 0 and 3, and you're having the values of the. You can see the numbers looks weird. Sometimes it's 400. Sometimes it's -1. Sometimes it's like 700, and you can see that it's the error start to increase. So the error instead of to become 100, 150. So that's mean this way you are not converging. You are not going to find the roots. So what you need to do, stop all this, and that's mean this way of arrangement is not good. And what you need to do is define a function other case instead of to rearrange to rearrange based on this x. Then we will see the value of x, the value of if see that the error start to decrease. So this means you are going to converge and you are going to find the roots of the equation. So this is the meaning of point number two. Okay, modify the function into another form. Okay, that was for the simple fixed point methods. The second method for today is the Newton-Raphson method. Newton-Raphson methods, it's most widely used methods. It's based on Taylor series expansion. And I think most of you remember it's the first week of introduction, we were talking about the Taylor series expansion. It's helping the engineers to reduce the error because the number of the terms that you are using. So Newton-Raphson method, actually, this is the equation that we are going to use. So don't worry about how we derive these equations. You're going to be asked. The equation is going to be given in the appendix. know how we came with this equation, but this is the way how we came. We are arranging the function of the Taylor series based on xi plus 1 to get the first derivative. So we solve it for xi plus 1. So we put it on the left side in here. So we are getting the Newton-Raphson equation. So as I tell you, you're not going to be asked to derive the equation is going to be given. But you need to know that to find the new value of xi, you have the initial value minus the function over the first derivative of the function. Okay, this is a Newton-Raphson method. This is how they are trying to explain this one in geometrical interpolation. Okay, no worries about it. You just need to get that this is the Newton-Raphson, the initial value minus the function over the first derivative of the function. Okay, Newton-Raphson is widely used and it's more efficient. It's more faster than the fixed point iteration, and it's more faster than the bracketing methods. But sometimes Newton-Raphson is having some limitations or slow converge. This is based on the function itself. So let's say that you are having some function like this way. You're starting from x0. And x0, because you are having the first derivative, so the slope is going to be shoot into a different locations away from the root, which is actually your root is supposed to be here. So the slope again is going to be shoot into x2 in here, and it's away from the root. So that means it's sometimes based on the nature of the function. Consider the Newton-Raphson is slow convergence. And this is some of the cases that Newton-Raphson is going to be poor acting on some functions. Like this case in here, all the slopes, they are shooting away from the roots, and the root is really far from there. Or when the function is having multiple roots, like this function in here, it has a multiple roots, so Newton-Raphson cannot solve this. Or the function actually not having a root, and never his action cannot solve anything here. So let's start with the Newton-Raphson and to see how to solve with the samples that we had. So we are going to use the Newton-Raphson to estimate the root of this function. And we are going to use the initial value of xi is equal to 0. And you can see from the example here is asking you to iterate until the true percentage relative error, that's meaning you want to calculate the ET, is less than 0.05%. And it's giving you the true 0 this here can be equal to 0. So this is what we want to achieve. So remember, it's based on the Newton-Raphson to find xi plus 1. It's equal to the initial value minus the function over the first derivative of the function. So we have this, we have x, and we have the function. Still, we don't have the first derivative of the function. So we need to differentiate the function first. So differentiate the function is going to be equal to negative exponent negative x minus 1. So this is the first derivative of the function. Okay, this is the first derivative of the function. Once you have it, then you can start to solve for the Newton-Raphson to find the new value. How to do that? Let's go step by step. Okay, so this is my function. And this is the first derivative of the function. So this is the Newton-Raphson. And so this is how it's going to be looked like. To find a new value x is equal to the initial x over the first derivative of the function, which is this part, negative exponent negative x minus 1. So our initial value, remember, is x is equal to 0. So you are going to put zeros in here. 0, 0, and 0, and 0. So when you put the zeros, when you put, so the first answer is equal to 0. So now when you go for the next iteration, equal to 0, it's equal to 0. We're going to use this value x is equal to 0.5 minus 6 point negative 0.5 0.5 or the negative exponent. So the answer is 0.566. So again, when you are going to go for the next iteration, x no more is equal to 0.5 is equal to 0.566. So this one will be go for the next iteration. So 0.566 minus all, so you're getting the answer of 0.567. When you are looking at these equations in here, remember for the fixed point, we need to iterate about 10 iterations to find the answer. In our case in here, remember it's our true value. Our true value is 0.56714. Our true value is 0.56714. 0.56714. This is our true value. Look at the third iteration. What's the answer we are having? It's 0.5671. It's almost equal to the true value. Within 3 iterations, we already solve, and our error it's even more less than 0.05. Remember, the question is asking you to iterate till the error is less than 0.05%. Actually, it's after third iterations, our error is 0.000002. Okay, you already found the correct answer. Okay, I will give you about 5 minutes. Try the example. If you have any questions, please do ask. Please don't forget to calculate the error to see. So just only 3 iterations, you are going to get the same exact accurate answer. That's why we are saying here it's the Newton-Raphson. It's widely used and it's common and it's more efficient. Please try. If you have any questions, please do ask.
Sir,
Yes.
so the main purpose of Newton-Raphson method ni is to find when the situation is diverged, like that, or
Converge. Converge. Converge, that's mean
converge.
you can see it's the error is, you can look in here. You are starting with the initial value of 100. So the error next time it's 11. So you can see it's reduced. Combine this value. If you take this value 0.5671 and you put it inside the function, so it's e negative 0.5671 minus 0.571, we'll get the answer is equal to 0. Remember, the value of x, this value of x that make my function is equal to 0. So this is the value, which is the true value. It's making my function is equal to 0. So most of the time, I'm trying to achieve the value of 0, converge to 0. And from my way in here, when you look even at the values of x in here, it's 0, 0.5. The numbers is near to each other. That means you are in a form of convergence in order to find the roots. If you find the values in here, it's really weird. Sometimes jumping to negative, positive, high value, lowest value. That means also your error is going to be really weird. So this means you are diverge. So most of the time you target to converge. Okay.
Okay, thank you, sir.
Okay. You're very welcome. Okay, do you something to give you advice if you are having like a midterm exam? I don't want to waste your time actually. If you are having some questions is coming from the part of the finding the roots of the equations and you need to iterate, is just only you can simply show one calculations. Let's say that you're going to show this calculation and how to calculate the error. So AT is going to be equal to true value 0.56714, 0.5 over the true value is 100. You show this is going to this form, and it's going to be sometimes is confusing which value that you want to take. In your case in here that you know is the first value is 0, and second value is 0.5. The next you need to use 0.5 into the second to get this and this. So just only an advice. Most of the time you can show just only sample calculation, and the rest of your answer you can put it in a form of a table. And most of the time when we are solving, please remember that we are using decimal points. So 4 decimal points. Okay. Don't write in a form of fraction. So we are using decimal points. I think there's something wrong with the course forum from the U Future, and I think they are accidentally deleting all my forums. So I think I will need to upload it back again. So maybe this afternoon you are going to find week 3 and some videos about week number 3. I'm going to upload back again the forum. Okay, any questions about the Newton-Raphson? Getting the values?
No
If the
question.
okay. So last method for today, it's the second method. So second method, it's a slight variation of Newton methods for the function whose derivative are difficult to evaluate. So for these cases, the derivatives can be approximated by the backward finite divide difference. Okay, what he's saying in here, Newton methods, we need to use the the derivatives. Remember, it's xi plus 1 is equal to the initial value plus the function over the first derivative of the function. So it says here, second method, it comes because we don't want to use the derivatives. So we don't want to use any derivatives because the derivatives are difficult to evaluate in somehow. But if we are not going to use the derivatives in the second methods, we are going to method the, the derivative backward finite divide difference. Backward finite divide difference can trigger for which value that we are looking for. Most of the time, we are having the initial value of x, and we are trying to find xi plus 1, right? So the initial value is given, and most of the time we are trying to find xi plus 1. So xi plus 1, this is considered is full finite divide. So second methods, it's using the backward finite divide we are talking here about. Anyone?
Sorry, sir, can't hear what question that you asked just now. Can you please repeat the
Okay,
question?
sure. Most of the time we are trying to find the roots of the equation. We are having the initial value of x, and we are trying I plus 1. But we are saying here that it's second methods. We don't have to use any derivatives from the Newton-Raphson. We are going to approximate the backward finite divide. So what type of value we are looking here for the backward finite divide? What's the backward divide? Looking for what value?
X I minus 1.
X minus 1 is considered infinite divide. Really is the infinite divide. Use Okay. So we come here, we are using xi minus 1, and we are using the value of xi. So remember, there's one thing that we said at the beginning, that it's open methods. It requires single initial value, but the is second methods, it needs two initial values. I minus 1, it's going to be given, and xi. So these two values is going to be given. So second methods, it will requires two initial values, xi minus 1 and xi. These two values is going to be given in the questions. But I think some of you now, they are going to ask, sir, you said is open method, it's just only one initial value. The second methods, it's need two initial values. Why we are not saying that is second method is a bracketing method? We are not saying it's second method is not a bracketing methods because the root it's not between them. Like in my case in here, this is xi and this is xi minus 1. But actually the root is not between these two values. See, the root is here. So that's why it's not considered as a bracketing methods. If xi minus 1 here, if xi minus 1 here at this position, yes, this is considered a bracketing method. But now you can see second methods is not necessary to bracket the roots. That's why we classify it as open methods. Is it clear?
Sir,
Yes.
so maknanya as long as the root is not in between, so kita kira dia sebagai open lah sir, open method.
Exactly. Because remember that we are saying one condition for the bracketing methods that you are having x lower and x upper, and xr it must be between these two values. So that means you have to get it into this form. Here is x lower and here it's x upper. The root must be between them. But in my case in here, as you look for the second method, is my xi initial here and my x minus 1 is here, but actually the root is not between them. The root is somewhere else. So that's why it's not considered or classified as a bracketing method, even though it has two initial values. Okay?
Okay sir.
Okay, so now let's see here what's the properties or the characteristic of the second methods. First, it requires two initial estimates. So that means you are going to have x and also x minus 1. But however, because the function is not required to change the signs between the estimates, it's not classified as a bracketing method. So second method is not considered as a bracketing method because the function no need to change the sign. So since now second method considered as an open methods, conversion is not guaranteed most of the time. That means when you are trying to solve, sometimes you are going to find is the answer it's giving you weird number, so it's divergent. So conversion is not guaranteed most of the time. Two initial values. The backward finite divide and the initial value of x. So it's asking to iterate until the x is equal to 1. the percentage relative and 0. So let's start to solve. Okay,